EnviroExpert is pleased to introduce John Soule. He is the president and CEO of Columbia Technologies and the director of Columbia Technologies do Brasil Limited, both global technology firms. He has managed over 2,000 high-resolution direct sensing projects around the world over the past 25 years. John holds 3 US and 2 international patents involving direct sensors and the use of real-time information systems. He is a 1972 graduate of the US Naval Academy with a degree in engineering and holds an MBA from the Chaminade University of Honolulu. John is a member of ASTM International and the Sustainable Remediation Forum. The title of John's presentation is Tracking Diffuse Groundwater Plumes with Low-Level Membrane Interface Probe Technology. John, it's in your
Take it away. Okay. Well, good afternoon, good day, and even good morning, and maybe good evening to anyone who's with us today. Thank you for joining, and thank you to Lowell for putting together and sponsoring this series of webinars. We do have quite a number of slides, but we do want to make sure we take breaks for folks to be able to ask questions, and Lowell will be kind of helping out with that as we go along. So Columbia Technologies, as Lowell said, we're based out of the U.S. and Maryland with operating companies both in the USA and Brazil. And we've been in the high-resolution characterization business since the beginning in 1999. So we've seen a lot of things work, a lot of things not work. And while membrane interface probe has been around for almost that entire time, some new developments in the low-level systems and the incorporation of the hydraulic profiling data tool has given us an opportunity to really go from the source area characterization that MIP is known for out to the leading edges at our MCL levels of drinking water with contaminants. So what I want to do is kind of give you some insight into the differences, what to look out for, what will work, what won't work, and as we go along. So I've got an agenda here. It's pretty straightforward. We talk the MIP, we're going to talk hydraulic profiling, the combination of those tools. Then we'll talk a little bit about the low level and some assessment strategies on how to use a tool in a groundwater plume type of scenario as opposed to source area, and some thoughts about building the CSM, and again, we'll have multiple opportunities for Q&A. The real challenge for all of us in the industry is dealing with the heterogeneity of the subsurface, whether that be the geologic heterogeneity, the chemical, the biological, or the hydrogeological. There is a lot of it down there. And so the challenge becomes what level or what scale of information do we need in order to have an sufficiently accurate conceptual site model to meet our project goals, whether that is a characterization, whether that's a remedial design, whether that is a groundwater control, whatever it happens to be. And we've all gone through the growing pains of the changes in technology and the changes in that scale and what information has been made available over time. But what we have learned, and I'm going to refer to the several ITRC slides in here as they conduct a number of excellent training sessions on these topics. This is one of the cartoons of the various the heterogeneity that we see down there, where we're dealing with low permeability zones, we're dealing with medium permeability zones, and we're dealing with high permeability zones. And what we see now when we go down with sufficient scale is a lot, are these isolated high permeability zones, which the transfer of the mass from a site will be highly preferential in that pathway as opposed to being stored in some of these low permeability zones. I took the liberty of borrowing from Dr. Tom Sales at Colorado State. Available on the web is this video that really illustrates this issue of heterogeneity in a test tank type of scenario. And then I'll show you some examples of how we see this in real life. But he's built a test tank with sands, clay, sand, clay, sand, clay, with these zones of higher permeability and lower permeability, and injecting a dyed water source on the left-hand side of your screen and letting it permeate through the permeability zones and being collected in a quote-unquote monitoring well on the right-hand side of your screen. And so this is characteristic of what we would call a young or recent release of material. And then the release is stopped, and we see the permeability zones of the larger grain, in this case sands, clean themselves out, but we see what is residual material coming out of these stored zones or storage zones. And this is commonly given the name back diffusion today, and we see that reflected over here on the right-hand side of the monitoring well. So it's this mature back diffusion of materials that we are frequently besieged with in terms of difficulty of trying to resolve on sites that have got low level but persistent groundwater plumes. And so this kind of does a nice job of illustrating that very quickly. The second point made by that information is the mass, the mass that we're talking about, the contaminant loading is really in those tighter grain soils and not in the groundwater, even though much of our industry and rules and regulations are centered around the groundwater concentrations. The mass is actually retained in those tighter grain soils. So the question is, what kind of tools, what kind of sampling approaches, what kind of data gathering approaches do we have at our disposal to take a look at that? And so I'm going to introduce the old guy of the toolbox here, and that's the membrane interface probe. Again, it's been around for 25 plus years. It has gone through a lot of modifications and changes over time and improvements, I would say, different sizes, different shapes, different additions, and now repairable, field repairable features on it. But the basic concept is there's an inert gas coming down from the surface. Typically it's nitrogen, and it sweeps past a small chamber on the bottom of the probe, which is separated from the soil water vapor matrix out here with a membrane. It's typically Teflon coated over across stainless steel, and we surround it with a heater block, and we heat that zone to 120 degrees. And some of the basic fundamental protocols about operating the MIP is heat that zone for the same amount of time every time, and understand that whatever's essentially at 120 degrees centigrade, that's your boiling points of your compounds, or what's the vapor pressure of those compounds. Do they have sufficient vapor pressure at 120 degrees? Are they a size that will come across this membrane? Are they hydrophilic or hydrophobic? Will they transfer all the way up this membrane and make it to our gas chromatograph detectors at the top of the borehole? And to prove those points, you need the performance testing that's required by the ASTM guidance. But essentially, if you're going out to use it on a site, make sure that you've got test data and you understand that it's going to do the job for what you're looking for out there. That's the basic MIP. It's, like I said, it's been around for a long time. When used in a standard screening mode per the ASTM and the standard operating procedure, the gas carrier gas is set at about 40 mils per minute running down that trunk line. And it's continuously monitoring as we push it, but we stop nominally at 1 foot increments and heat those zones for a consistent period of time. And that really will control your production rate right there. And then that carrier gas goes up and continuously feeds across one or more gas chromatograph detectors. We typically run a 3 detector suite, which includes your standard photoionization, flame ionization, and the new detector, the halogen specific detector. And display here on the right is a typical response to a trichloroethylene test standard at 1 ppm and at 5 ppm, and you see a relative response, fairly linear response between the two concentrations of the test standard. The ASTM calls for an aqueous phase test, and that basically tests from your membrane all the way up through your data acquisition system. And we recommend that's done on every borehole, before and after every borehole. Typical responses that you get out of a membrane interface probe. Again, I'm showing two detectors of response here, photoionization in blue and halogen specific in green. The fact that the two of them occur at exactly the same profiles and exactly the same depths tell us that essentially we have a chlorinated or halogenated ethene in that contaminant. And what MIP does really well is tell you the depth of where the occurrence is. And it gives you some degree of relative strength, though it is not a quantitative tool. It is essentially depth versus VOC response. And it is a total VOC response. So if this happens to have PCE, TCE, DC, and vinyl chloride in there, all of them are going to respond on the XSD. Not all of them will respond on the PID. So again, the key point there is it is a depth for VOCs versus depth response. If you have a fuel where you don't have a chlorinated compound, then you're going to get an FID-PID response. And again, we're going to get depth versus response versus depth. And then notice we have a little bit higher FID response up in here, which is probably something to deal with a vapor phase or possibly even a methane on the MIP. So MIP is giving us an indication of VOC, again, use that 120 degrees, vapor pressure, hydrophilic, and that's the kind of compound we're going to see on the MIP. And it's present in 80% plus of our sites out there. I put this in here to show you the calibration or the performance test build on a different MIP system. So this is different lengths of trunk lines, different diameters of trunk lines, and different materials of trunk lines. That's that line carrying the inert gas from the detectors back up there. And this is from 100 ppb up to 10 ppm test standards. And the reason I put this in here is just to kind of give you a sense of comfort that a MIP system with a clean trunk line and a standard membrane running with a standard flow rates will give you a predictable linear response on the instrument. So if it's operated with a standard protocol, then the variability that you see in the MIP should be a reflection of the heterogeneity of the subsurface. So this is where we've got a good response. So this is a good background on the basic MIPs. Let's just take a second just to see, do a quick poll on basic MIP before we continue. Lowell, if you could do that. So just quick check your familiarity or experience with using standard MIP, so I kind of can base the rest of the conversation on that info. So just take a quick minute and fill out the poll for me if you would, and we'll give it just 30 seconds. Get those pens and pencils out there. Vote your conscience. Okay, we've got another 10 seconds and we'll drop it off here. I see Lowell put the term accuracy in there. Way to go, Lowell. Now, what is accurate? Okay, so let's end that poll and we'll come back to some of those conversations later. So that's good information. Again, I'll stress that that is a qualitative tool. It's a screening tool, and we'll talk about it in some sort of semi-quantitative basis here using the other lines of evidence. Let me introduce hydraulic profiling tool. Hopefully, you've seen some of this work out there. I would go so far as to say today, I don't know how one characterizes or does any sort of remedial design plan without using and understanding the heterogeneity associated with the hydraulic permeability, and HPT does a great job of providing that. It's a simple concept. We take a tank of water at the surface, connect it to a flow control pump, where we essentially try to maintain a constant flow out a screen just above the MIP profiler. and push that into the subsurface, and it measures continuously the resistance pressure. And so what we have here is pressure versus depth going on at the same exact time we're measuring those chemical responses versus depth. The HPT also has electrical conductivity on it, as it's been used with the MIP over years, and EC's used either alone or with other direct sensing tools. But now we've added this active pressure measurement of the formation, and so it gives us a feeling or an understanding of what the resistance is in the individual soil pores as we go by them with the HPT. And a lower pressure on the system means there's less resistance to the water flow, and therefore it's going to be a more permeable soil. And a higher pressure is going to say, well, we've got a less permeable soil. If I just said that, it's more permeable and less permeable. And so it's pressure versus depth, actual hydrostatic or water pressure. And if you push this down through a long borehole down to 100 plus feet, you'll see a nice hydrostatic pressure curve develop as the baseline of this as you push it all the way down. Beautiful sets of logs. I'll show you some actual data here in a little while, although this is actual data. What's next in the HPT side? So now if we combine the MIP response and use a combined tool, MI-HPT, I'm sorry, my apologies. You see we take that PID XSD response we had earlier in those 3 different intervals, and we look at that compared to the pressure response. What we see is this is likely more potential transport in this more permeable zone of this response on the MIP, and this is likely more storage going on, or just like we saw in Dr. Sales' video. This is that stuff that's going to back diffuse on us as we try to clean up the site or clear out that low persistent groundwater. This is a great illustration of that data set, of that phenomenon going on with actual field data here with the MIP. So we've got MIP response, PID XST later up against the HPT data coming in at the same time. So that's where we are. So that's the added advantage of HPT. It can be used alone. It can be used in combination with MIP. It can be used in combination with sampling. We'll take it to the field in any of those combinations and recommend you really take a look at that HPT data. So let's do a quick poll on HPT global and just see what our experience is on HPT. So here's, if you take a quick minute to answer the questions on HPT, I'd appreciate it. And I think there's 3 questions there. And then we'll just give it 30 or 45 seconds and drop it back out. We'll point out, as one of these questions does, that the tools that we're talking about today are generally direct push tools, whether they're used with a percussion type system made by Geoprobe or AMS or another company, or whether they're used on a cone penetrometer system where they're being pushed in at, based on reaction weights. So therefore, they're not really built yet to go into any of our more competent limestones or bedrocks or something of that sort. So we are talking about unconsolidated materials where we're doing most of this work. Okay, let me drop that poll off and we'll talk about low-level MIP. Okay, what has changed with low level, and I'm going to borrow slides here from the Geoprobe. Geoprobe is the developer of this family of tools. They're deployed around the world and they're available to you as practitioners out there. What I'm hoping to do is to help you know what to look for, when to use them, when not to use them. What low-level MIP does is basically give us a factor of 10 increase in the detector sensitivity by modifying the gas flow in the trunk line of the MIP system. And so we basically drop in another box. I think I got to put a box in the middle of the system. So this would be our normal trunk line flow. And it would normally have gone past our GC detectors over here. But what we're going to do is now control essentially starting and stopping the flow of this carrier gas. And I think the next slide does that. So we've got our 120 degrees down here on the bottom of our borehole. And this is tied up against the soil water air vapor formation. And what we're going to do is we're going to stop the carrier gas. See if my little pen will work here. Pen. So we're just going to stop the carrier gas with the control system and let the mass build up across the membrane into this detection chamber here. And then when we restart the gas, then we have more mass per that unit volume of gas in the trunk line that then gets injected across the GC. So it's very similar to a purge and trap kind of concept that you're used to in the laboratory. So how do I do? So what we get now is a slug of gas coming through with much more mass in it. And now we're looking at, this is a standard MIP response, same curve we did a while ago. We had basically about 10,000 microvolts of response above baseline for 1, 40,000 for 5. We do this with a low level system. And now we'll look at this is be the baseline we're working with. And now we've got basically, this is a 10 ppb or 10 micrograms per liter concentration. This is a 25 ppb. And you see we have noticeable signal to noise here at 25, and it increases at 50, 100, 250, and 500. So we're now down that order of magnitude below the standard MIP response, and we're getting detectable information on the MIP itself. Now, the next point I want to make is an extrapolation of this understanding. So this is what the system itself is doing with its performance, and we can show that that's repeatable and linear in response as it grows up there. When you put this in the formation and add the benefit of the hydrostatic pressure of the formation and the fact that we are focused on a very small interval of the compound, minimizing any dilution of the groundwater or the vapor, we're going to actually see lower numbers or see higher numbers in the formation than what the system is saying here. So I'll show you some examples of that here in a second. So here's a low-level MIP testing. We looked at the regular MIP a while ago. So we're down here at 10. This is 10 ppb. This is 5 ppb, and we're going up to basically 1 ppm here. So you can see, again, we've got consistent linear response. This is actually a very long trunk line that we can use for some deep boreholes and deep groundwater tracking. So again, what low-level MIP is doing is taking this sort of diffused baseline by a constant gas flow and starting and stopping the gas flow and concentrating the mass in there. And so we're going to get this sort of porcupine curve that's showing where the concentrations, this is each of the 1 foot intervals, but with that gas start and stop reaction shown on the graph. So that's the big difference between a low level and a standard MIP, is this modulation or control of the gas flow. What becomes very critical is this gas flow is only open or on for a certain window of time. So much like chromatography, we've got to time this window correctly for the compound of interest for the site that you're looking at. So it's very important that you review this with your vendors, that they show you the test data for the compounds that you're tracking on your site, and you've optimized the response for the compounds of interest. And if you've got multiple compounds, then that has to be addressed for your individual site. So it's not a standard operation out there. It does require an application of good science and method verification in order to use the system. So now we've talked about regular MIP, when we might use low-level MIP and the added advantage of the HPT. Essentially, as we started with the conversation, we're starting with geology as our primary driver. We're going to need to use multiple lines of evidence to deal with the heterogeneity that's down there. We need to track what each data collection method is giving to us in terms of data quality objectives and the uncertainty associated with that. Know the limitations of those systems. Good example would be a MIP is not going to show you an SVOC, say, for example. understand the chemistry that's coming up. Are we looking at ethanes, ethenes, yeah, multiple chlorines or single chlorines, that sort of thing. And then the real important point, though, is as the ASTM does, as the SOP specifies, verify the performance of the systems that you're using out there as you engage them. Thinking about a site then, moving from the source area characterization role that MIP played in its early days, moving to a more of a diffuse groundwater plume. Oftentimes these cover large expanses. An advantage of a tool like MIP is you can cover a lot of geography quickly. But we need to get it, we typically approach that in a transect perspective. So we lay a transect out from clean to clean and then across the plume. And we're looking for those higher permeability zones where we've got higher mass groundwater flow, and we're also looking for where we have the highest contaminant concentrations, which are going to be in those stored areas. So we want to separate that heterogeneity across the transect and look for those approaches. So we'll typically start with what I call reference points on the known source reference points from the historical conceptual site model, validate those points with a handful of high resolution points that could be both something like MIP, HPT, and individual discrete samples, measure that up against the monitoring wells and know what our anchor points, our reference points are in order to start the conceptual site model development here. Bound our source area vertically and horizontally, and then approach our transects as we were just looking at it. This could be pathways associated with down gradient receptors. It could be just a direction groundwater control, or it could be property boundaries, whatever happens to be the particular boundary conditions we'll need to evaluate. Once we have those zones identified and where the mass is and where the flow is, then we go in and sample that. And there is, in our approach, there's always a high resolution sampling, a component that goes in on the end or the tail end or as a part of our high resolution characterization. And from those samples, we can get actual contaminant ID, we can get mass numbers, we can get groundwater concentrations, and any other parameters we may need for remediation design. From that, we can typically start to identify. So this is a cross section of one of those transects, and you can see we have got multiple high resolution points in there. So MIP is going to give us a relative number, qualitative number about mass or contaminant mass or contaminants down there, and HPT is going to give us a quantifiable estimated K value. If we go in and do the high resolution sampling, then we're going to come up with actual mass and concentration numbers. And with those combination, we can now start to look at where is that high permeability or transport flow path, as you see illustrated here in this particular cross section. So this is an MI-HPT with sampling data to go with it. Let me look at a couple of site examples. So I just kind of want to show you again some data compared to each other. So this would be standard MIP data over here and what it might look in a continuous profile mode. And then over here you see those start and stop of the gas flows, or what I call the porcupine plots over here. And the concentrations here where we have known response on the MIP, we're looking at, again, we're down at PCE of 0.2 and TCE of 5.5. And that's basically what this aquifer's got in it over here, is about 5 to 20 on the TCE side, 24 down here. And that's the type of plot we'll see down there in terms of depth response and the low-level MIP. Let me jump out of this presentation for a second and just bring up a couple of other real-life transects here for you. Are we starting this poll? Okay, so let's just do low-level MIP poll here for 30 to 45 seconds first, and then I'll show you some other data, if you would, please. I think we're running pretty good on time here, and so we'll have time for questions as we get through the next step here. Let me turn on some labels. Okay, another 10 seconds and we'll wrap this one up. Many thanks. And Lowell will send you out some follow-up on those polls and links to the presentations as we finish up here. So let me just pick 3 low-level MIP points in a transect down here, LO1, 2, and 3. So we're going to display multiple lines of evidence. My clicker finger is not working here. Multiple lines of evidence here in our data sets. Let's see if I can bring that up for you. And so this is a typical 3-point transect across that. And what we're looking at here is we've got multiple lines in here. We've got the MIP data in here. We've got the HPT. This is K value that's in here. We've got the electrical conductivity, and we've got PID and exodus. So I'm going to split these apart by unstacking them. And it gives us a feeling what that transect looks like in detail. So what do we know? Well, we see repeatability on our MIP, XSD, and PID. So that tells us we're looking at pretty much the same compound. The profiles look similar. And you can see that's low-level information based on the sort of the porcupine look. K value is giving us a pretty consistent number here all the way down. We're not seeing any big peaks or valleys in that small hole here where K drops off and EC goes up. So it's a little bit of a tighter grain component there. We have another one over in this location here and some more over in here. So this is what our profiles told us across that transect. Now we went in and did these high resolution sampling. Here's a couple sporadic samples. We're looking at TCE 1.2 and PCE, tetrachloroethylene, at 5 micrograms per kilogram. Down here at this elevated response here, we're at essentially drinking water or non-detect levels there. These all look 0.2. This one's a little higher. We got 0.52 micrograms, 0.2, again, 1.3 here. And so this is real world data for the kinds of responses where we're seeing positive low-level MIP response, and our contaminants of concern are actually below 10 micrograms per liter in this particular case. So that's an example of some real world data we pulled in. I think I have another one in here. Let me clear that selection and pull 6, 5, and 4. So here's another set of 3. This is a different soil condition, different site, if I remember correctly. And you see our K values have got some breakup. So here we've got some of that tighter grain, tighter soils, less permeable soils, and we've got a little more heterogeneity going on down in here. And we've got a stronger MIP response over in here than we do over in here. These concentrations are running, says in D, so that's kind of comforting with our MIP. These are running 12 micrograms per liter on the cis. That's your single, actually 2 chlorines in that. Tetrachloroethylene is about 2.5 here, and down at the bottom, tetrachloroethylene is running 2.5, TCE 2.5, and cis is running about 29. So you can get a feel for what your real world levels are with the MIP response out there in the low level mode. So that's kind of what I wanted to just show you, some of that real life data. So kind of a summary here, what I want you to get out of it is use a systematic approach, understand the chemistry that's out there, and validate or verify your system performance with whatever sensors you're using out there. And when I say systematic, I mean use a scale of measurement that is consistent across the profiles, whether that be transects or whatever you're using as we go along. So I think we're right at 40 minutes, so I'm going to stop there, and Lowell, maybe you can help us out with the questions or how you want to handle that.
Yeah, so we did get a question in follow-up to the last polling. It's regarding regulatory acceptance. What level of acceptance are you seeing from regulatory personnel to use this as a tool in refining understanding of TC subsurface conditions where this contaminant of concern is a reopener at RCRA or surplus sites?
Well, there's a couple aspects to that question. So what we're seeing at the regulatory level across the country and actually also in Brazil is that when there is a collaborative team and engagement on evaluating these broad diffuse plumes, and we're trying to get a sufficient data set to understand a broad diffuse plume gets very expensive, then higher resolution tools that can cover a lot of ground actually get a lot of, they're very appreciated, I guess is what I would say. I haven't seen them applied to the concept of a legal regulatory framework of we're going to reopen the site based on the fact that low level saw something that we didn't know about. But I have seen it used on a number of sites really as a diagnostic tool. In other words, we've been beating our heads against this site now for a couple of decades, and we still haven't quite got our understanding about it, and our monitoring wells are saying this. And what we're finding is so many of those monitoring wells are not aligned as well as they should be with those hydraulic profiles and the chemistry profiles that we're seeing down there. So we're really using these tools to fine-tune and better define those complex sites, is what I'm seeing. And for the most part, we're seeing good response on the regulatory side.
I noticed that there were a couple more folks that potentially had some concerns regarding deploying this technology, and I'd like to encourage those folks to submit your questions through the Q&A discussion with the link located at the bottom of the page of the presentation window. And anybody else who has any questions, please submit them now. Now is a good time.
Yeah, so I see a question there. Best way to correlate MIP data with actual concentrations. I'm a big believer in keeping the scale of your measurements comparable. So if we're going to be looking at 1 foot increments with a MIP type system, make sure you're trying to get down to that same scale in your groundwater or soil samples. I'm a very big believer in very discrete on-core, terra-core type samples in a systematic basis across your areas of concern. So say, for example, in this plot that's on the screen, if I wanted to carefully look at this MIP response area right down here, and this is fairly deep, this is down 35, 45 feet, I would core that typically with a dual tube system and bring it up and then systematically take 1 foot, 6-inch cores all the way down there and measure that in order to get an accurate mass calculation of what's actually in there. Don't, get rid of the old handheld PID screens and that sort of stuff. Then your best correlations are going to be to lay the lines of evidence out vertically and horizontally in terms of, is this about a 20 microgram per liter plume in this area? And then underneath it, we see more of a vinyl chloride plume from the remediation. And you will see separation of your different compounds. So remember, MIP is going to measure a total VOC, and it's depending on your detectors, it may not see other VOCs that you're being measured in your groundwater. So make sure you're comparing apples to apples in terms of your data correlations. After that, your correlations are going to have difficulty based on the media effects of the different soil types. So, question on combining MIP with mass spectrometry. It has been done, can be done. The question that you have there is compound identification, which mass spec does quite well. So you can pull this gas off the MIP system and drop that into a mass spec if you have sufficient mass. You'll then get the added advantage of an MSD detector. So yes, that can be done. It's an expensive way of doing it, but can be done. Can they be run with CPT? Absolutely. You are stacking up a set of sensors, so you have to think about the site conditions that you're working with. You are putting a very expensive tool rod down the hole, but also remember they're separated by elevation. So if your bottom rod bottoms out on bedrock and your DNAPL is now not being looked at by a MIP system that's 3 feet above that, you may not see the DNAPL sitting on the bedrock if there is such a beast out there. So again, you have to think about your data quality objectives and how the tooling, which tools and which sensors would be appropriate. But we have run them in both configurations. So thank you, Mr. Whitley. Queenie, is case studies on petroleum? Yes, quite a number of those. We have been employing specifically HPT, but also MIP in a more standard screening mode on petroleum sites, and it is very useful on specifically older gasoline sites where you don't have much of the PAHs left out there, and so we are seeing quite a good use of these tools on the contaminated sites. Be happy to give you some case examples on that. Has there been much uptake of these technologies in the cost-sensitive, non-regulatory, due diligent ESA market? On the due diligence side, Trevor, I don't think so. It is a very cost-sensitive world. What we do find is when there is money to be spent on characterization and, better yet, the phase 2 or the remediation part of it, it does not make sense. Basically, the business case has been made. One does not want to start trying to clean something up if they don't know what the problem and where the problem is. So in a straight due diligence, hey, I want to buy a dry cleaner site. If I was buying it, I'd want to use the tools. If I was selling it, I wouldn't want to use the tools, to be very honest with you, because they are, the data, the statistics are not in the favor of the dry cleaners on the sales just because of the configurations out there. Significant fill is an issue. You fill up the sites full of concrete and old cars and whatever's. That is a difficult issue with direct push tools. If we're tackling that kind of site with a landfill, we'll typically use what we call a dummy probe and make sure we understand the area we're working in, and either probe a dummy probe and then go in with the sensors adjacent to it, or we'll do it very carefully, or we'll have to think about it. But that is surface conditions and access are always, as well as the subsurface fill conditions, are very important. Low-level MIP run the cost the same as a normal MIP. It should. I can't say that that's true for everyone. It's another box, so there is some more capital equipment in there. The biggest difference, Jay, is the production level is slower because you're doing this gas cycling component. MIP's slower than HPT because you're doing the heating cycle, but now we're also doing a little bit of gas cycling and trapping. So you're going to lose about 20 to 30% on your production rates. And that's really the difference in the cost, is how much production gets done. But the cost on a daily rate should be about the same. And MIP use in hydrocarbons. That again has evolved quite a bit over the last few years. I would say we are using it extensively on petroleum-based plumes now, but with great care. And we could can talk about what does that mean. It has something to do with flow rates. I'm not sure I'd put the expensive halogen specific detector out there. But you can go sense, you know, a lot of stuff with PIDs and FIDs, particularly if you're considering the dissolve phase component of what's out there. So there aren't other tools other than sampling tools that will look at dissolve phase. Or we're seeing more of this petroleum vapor question. So we're, you know, obviously MIP will see that vapor very, very well. And so if there's a question, do I have a NAPL or a vapor component near an occupied building? That's it provides a quick answer on that question. So that's all the questions I see lined up. Noel, if I got them all or not, but appreciate those. They're good questions.
Yeah, I agree. That was good questions, good discussion. If there's any more last questions from the audience? There's one more.
MIP restricted dissolve phase or LNAPL? It's definitely not restricted to dissolve phase. And you have to decide, you have to make, what is your definition of an LNAPL? An LNAPL, you know, as defined by ITRC, is greater than 100 milligrams per kilogram in the soil or greater than a ppm in the well. And a lot of that will generate from a pathway from a source of LNAPL, and they are indicative that there is LNAPL in the site. And what we've found over the last several years is that a lot of money is being spent on the cleanup of petroleum sites without ever really defining where the LNAPL is. And so, yes, we have been using a combination of the ultraviolet optical scanning tool, the laser-induced fluorescence, now the OIP from Geoprobe, combined with MIP and combined with HPT, and the sampling is critical to really nail down the LNAPL characterization. And it's very thin, and it's out there, and it's very problematic.
John, I got a question, and it's regarding planning, project planning, and field planning. And a lot of times people, consultants and project managers are putting together an investigation plan and maybe don't have time to get into all of the details, but for feasibility, planning and budgeting, they might want to consider so many MIPs for a project that is either source area delineation or maybe plume delineation, or maybe there's the transition from one to the other, or if there's a potential receptor area that is of high, you know, really high interest or high risk, that maybe warrants more information. Do you have any rules of thumb or some kind of guidance on how many points you would place in the area of a source versus across the area of a plume, considering that plumes are pretty expensive potentially, and or, you know, high risk or high critically important sensitive receptor locations? How would you go about that?
Well, the way I would approach that is, first of all, start with the conceptual site model as it exists today, and what data do we have in it? Where are the data gaps? The second is, what are the objectives, business and technical objectives of what's going to go down? The third is, what are the geological conditions? You know, a diffuse plume in a sandy aquifer is a lot different to deal with than a diffuse plume in a tight grained aquifer. So your spacing and data uncertainty is much higher in the latter case. So it really needs to be a collaborative. You know, what do we need to do for data quality objectives? How much data do we need? What are our ways of getting that data? For example, we were looking at some of these deeper MIP plumes here. We were down in the 100, 125 feet range. Getting MIP to that depth is great if you can do it. If you can't, then you still need the data, so you're going to have a different way of getting it. So how does this tool fit into the sequencing of the data quality objectives, and how do we meet those objectives? So there isn't a one-size-fits-all at all. I think the most successful engagements and projects outcomes are when the technical team is talking about those elements. What do we know? How can we leverage it? What do we need to know? How do we get that data? And then how do we verify that we've got the right data? And it's going to be driven a lot by a number of factors. So, so it's hard to answer your question. I've had dry cleaners that take 6 months, and I've had dry cleaners that take a day. So it's just a function of a lot of different factors. What's the best way to term spacing for probes? Again, really kind of that same question. What are your objectives? What are your soil conditions? What do you know? What other information do you have in order to figure out your spacing? I'm kind of a take a big step kind of guy. Let's make sure we get it bounded, and then we can control the spacing as we work our way back in it. But let's make sure we know where the problem is, and we know what the outer edges is, and then we can start talking about the spacing in between. And again, a tight soil is going to take more points than a very homogeneous sandy type of aquifer. So I think we've got the questions that have come in on that. So again, I'd like to thank everybody for chiming in. We enjoy looking at sites. If you've got specific questions, shoot us an email, give us a call, Skype, link, LinkedIn, anything. We enjoy this business, the complexity that's out there, but most important, we enjoy working in a collaborative engagement with you all. So we're willing to roll up our sleeves and give you our best thoughts on how to tackle a project and what will work and won't work from our perspective. But we'll ask you a lot of questions about what you're trying to do, so that we'll play devil's advocate for you. So